When a human walks into a room, they experience sound, and they're very good at being able to convert that sound into a perception of reality.
Humans are limited to 2 ears, but there's no reason why a computer should be limited.
So in some ways, we can think that we're giving the computer supersensory power. Instead of just 2 ears, it now has maybe 20 ears. I've always been intrigued with sound. I used to like going in tunnels as a child and shouting real loud and hearing the echoes. I was fascinated by the bat, the way it navigates with sound and so forth. Loved playing around with stereos and radio equipment to make all kinds of noises and sounds. So I've always been fascinated with sound and just the way it moves, and also the way we interact with it, the way we perceive it.
By trade, I'm more of an electromagnetics guy, so I used to work on audio, electromagnetic simulations, antennas, radar, that kind of stuff. Many of the things that are standard procedure in radar are really somewhat obscure in the audio world, but nevertheless applicable. So that's why we were able to pull off some exciting stuff that hasn't been done in the audio field before.
Sound is change in pressure at a very high frequency, anywhere between 20 hertz at the low end, all the way up to 20,000 hertz. Some people can actually hear sound that high in terms of just changing air pressure, which means we compress the air, and then because it's elastic, it kind of comes back a little bit, so we get this what we call compressional wave. Right now, I'm changing the air pressure in the room with my throat. My vocal cords are slapping together, and they're creating this very rapid change in pressure. And it's shaking, that pressure is shaking the tympanic membrane, or your eardrum, which is now creating these neurons to fire in your head. And as a matter of fact, if people are listening to this over a TV, that signal is also pressing against the microphone and changing the capacitance of that, which is changing the voltage and being stored and now being reproduced on their TV sets and changing the air pressure in their rooms through the speaker system. So sound is essentially change in air pressure in the range that we can hear, which is about 20 times per second or 20,000 times per second. So I would say in the history of audio sensing, you really have to look at the history of audio and electronics. And probably the key development was the telephone with Alexander Graham Bell. And that's when the world became fascinated with the potential of how we can use sound and the way we can convert it to an electrical signal, because really the microphone changes the pressure waves in the room to changes in voltage. And once we get it into a change in voltage, we can send it on a wire and do all kinds of things with it. So, the people at Bell Labs were pioneers in this area in trying to understand the audio signal as far as it relates to speech. There were many, many contributions over this past century to that, but probably the most significant one had been the introduction of the microcomputer, because now we could elaborate on all this information in the signal. We can cut it into samples, we can study the information, we can apply some very heavy-duty mathematical operations to it to extract more and more information from the signal. So this really opened the door for a lot of research. And one of the areas of research was this notion of arrays. What if I have multiple microphones? And based on the way we know sound travels, it takes time for it to travel, we're able to capture the sound over many spatial positions and use that information to start to create images. Where did the sound come from? In our systems, we generally have smaller number of microphones, but we put them anywhere. And we integrate it with high-performance computing. In other words, we have distributed computers as well.
It's actually 11 computers mounted in a rack, and each of these computers has 8 CPUs, so we have 88 CPUs total. And the theoretical peak performance of this machine is around 800, 900 gigaflops.
This gives us a lot more flexibility in what we can do, how quickly we can change things and adapt to the environment depending on what we're sensing. So I think what we're trying to do here is integrate high-performance computing with these large arrays of microphones, as well as other sensors. One of the more exciting aspects of this project, the long-range goal, is this idea of what we call acoustic scene understanding. When a human walks into a room, they experience sound, and they're very good at being able to convert that sound into a perception of reality. In other words, in this room now, I can hear a vent behind me a little bit. I can hear a computer buzzing off to the side. I hear my own voice. That's a lot of data coming in. If I have a microphone in the room, the microphone is varying just like my eardrums are, but it's just picking up a dumb signal. And for the computer to be able to understand it on the same level that I can is still far away from us.
Things that come easy to a human are very, very difficult for computers, and we're still in the beginning of understanding how to actually model that so to enable the computer to get a better semantic understanding of the world based on the sensor signals that the computer gets.
We're taking some baby steps right now in terms of being able to set up sensor networks that will start to collect information similar to what the human mind does. What are the sound objects in the room? What's their meaning? And then find relationships between them. So sound source location is generally the first step. The microphones are taking in data. When a sound happens in the room, it takes time to travel to each microphone. And we use that information then to assess where the location of the original sound was. And so we could identify, first of all, that a sound source exists, and then assess its location. Here I'd like to illustrate a few of the contributions we've made to this area of distributed audio processing. Here's one example of what we may want to try to do when we have a room full of people. We want to find out where they're at so we can ultimately get their particular audio stream and separate it from everybody else's. The first step is this sound source location problem, which in this experiment here we have actual video images of what's happening below, and then above is this schematic that illustrates individual detections of when we detect a sound source in the room, and then it presents their location here on the image. For example, as I kind of sweep through here frame by frame, you see I'm kind of crouched down here, and as I'm making sounds right there, you can see this big dot which represents my XY position where I'm at and my Z position in space. And then we have another speaker, Hari Krishna, who's one of our grad students, also speaking, and he has a much softer voice. So if I advance the frame, you'll actually see when he makes some noise, a dot that corresponds to his position there. We can play a little stream live so you can actually see these detections here. Again, here you're starting with me. I'm saying something right here, but you'll find out as I say stuff, you'll see other smaller detections light up, and those will be false alarms or false detections, as we call them. But you can go ahead and listen to this. We also have someone else in our space.
Hello, I'm Hari Krishnan.
Hari, can you explain to the viewers what they're seeing in the acoustic image?
They're seeing different colors, dots, rendered on a 3D.
So this is a case of sound source location, and some of the challenges are we need to process the signals on the microphones to enhance our detecting of weak sounds, as well as suppressing false alarms or false positives. And we've developed a couple of contributions to that area. One is a special way to process the signal so it better uses all the frequency information in the signal. When sound travels, low frequencies travel better than high frequencies. And we've developed mechanisms to help the high frequencies make a better contribution without being overwhelmed by a lot of noise. And that's what we call our phase transform with this beta parameter that helps us adjust how much whitening or how much dependency on the signal phase or timing we use as opposed to the signal magnitude. And that's brought about significant improvements in sound source location. In this image here, what you'll see is an example of what the raw, what we call acoustic image would look like. Again, as we look through our space here, this would represent the XY plane. When we see these bright dots here, that represents the likelihood that someone is speaking there. And what people have done in the past is either this raw acoustic image where you really don't see many detections. As a matter of fact, it's so low resolution that you really can't identify a particular peak, which would represent the location of a sound source. Here is typically what people have done in the literature too, where they give all the frequencies equal weight. They just kind of bring them up independent of how much noise they may have in it. And you can also see a dot there. It's much better than this one that is mostly low frequency content, but it's still not quite as good as these two images here, which really represent our contribution in that we give this compromise between total equalization or total whitening, in other words, all frequencies have equal content, to one that more or less decides based on the amplitude of each frequency component in our signal how best to amplify it or have it contribute to the image. Beamforming is really the next step after sound source location, because once we know where the source is, Then what we do is we set the delays on all the microphones, which we do electronically with the computer, so that a sound emanating from the source or the point that we've identified will all come in phase. So if you can imagine sine waves or waves on a sea all kind of coming in at the same time, they'll add together to become a much stronger wave. Whereas sounds coming from other parts of the room are going to come at different times and they won't line up in phase. And so they'll tend to cancel out or on average not be as strong as the sound coming from our point of interest. So we beamform with timing by changing the timing on the microphone, so we strengthen the signal coming from there. That way it gives the computer an ability to get, once we beamform, a signal that really represents this source and not so much the other sources. And there's many techniques for doing that. You just don't simply change the time. There's some frequency, there's some filtering that you have to do associated with that. There's also adaptive techniques, so you can more or less sense what other noises are going on and somehow null those out.
So it's sort of like a directional microphone with, however, the added benefit that to actually change the beam characteristics and turn it towards the point of interest does not require any physical turning. Meaning that we're building the directional microphone out of omnidirectional microphones, and then again do the processing only in software.
Here's a case where I'm speaking in a room, and the room has a wall of microphones maybe about 3 meters away. And if you've ever done a recording with a microphone that's far away from the speaker, you'll notice you'll get a lot of background noise, and you'll get reverberations or echoes that kind of come in. It sounds like you're talking in a room like a bathroom where there's a lot of echoes, and you hear this noise in the back. And you'll hear this when I play this. You'll also hear kind of a lower quality voice signal on coming from me because, again, you lose a lot of frequencies when the sound travels from my voice to the particular mic. And here's an example now of just the closest mic on that wall to my voice. To get a film of lectures of someone just explaining. So you hear some noise in the background. Concepts, everything from circuit analysis through Fourier analysis. You hear my voice sounding kind of tinny. Information theory. And now what we've done here, I used all 16 mics in the second signal here to, again, do the delay and add them together so that I'll get constructive interference coming from the point where I was located. And here you'll hear a definite difference in the sound quality. To get a film of lectures of someone just explaining basic electrical engineering concepts. We virtually moved the microphone closer to my voice. Obviously the microphone positions didn't change, but through beamforming I was virtually able to put the mic much closer to my mouth and get a higher quality signal, reducing the noise and also giving me a much better sound quality. So it gets to be a pretty complex process, and we're developing software right now that's going to make it easy to assess many of those different algorithms. There's an effect in audio systems called the cocktail party effect, and it's something that humans do pretty well. Is when we walk into a room and, for example, a cocktail party where there's many conversations going on, we can somehow, in the midst of all that noise, zero in on a conversation that we're interested in and follow it, in spite of the fact that it may not be the strongest conversation in the room. So that cocktail party effect is something that humans can cognitively work their way through with a lot of cues, because we start to follow words, we can tune in on someone's voice, and we're able to distinguish that among the others. Whereas for a single microphone to do it, it's impossible. You know, you just get all these sound signals coming to the microphone. Even a human listener listening to the microphone after it's captured that way has a hard time assessing that voice again. You lose a little bit in that process of going from all these voices to one signal at a certain point. In this one, we're going to hear a female voice talking about her reading of folklore, and then you'll hear many other distracting voices in the background, typical of what you might hear in a cafeteria or some kind of a party scenario.
So I've been reading about all these different folk tales, and I've been thinking...
So you can sort of hear her voice. This is the closest mic to her out of these 16 mics.
Most of them are very region-specific. There's something about the culture. There's one that I've seen in Russian, Native American.
Then the party gets louder.
I thought, okay, everybody's going to be there. A man getting some sort of magical light.
And it gets harder to hear there toward the end. With many microphones, we can use this beamforming to focus in on the particular voice of interest. So now what I'll do is I'll beamform on her to hopefully suppress the other voices. You'll still hear the other voices, but what you'll tend to hear is now the female voice above all the rest, and it's a lot easier to follow what she's saying.
So I've been reading about all these different folk tales, and I've been picking a region to read folk tales from almost every week, and most of them are very region specific. You know, it's something about the culture, but there's one that
And here they get louder, but you'll still hear here above it.
American, British, and Arab folklore, and it all has to do with a man getting some sort of magical wife, but the condition is he doesn't ever hit her.
And of course, that's a bigger challenge now for beamforming, to be able to suppress these other areas and bring out the point of interest. So in some ways, we can think that we're giving the computer supersensory power. Instead of just 2 ears, it now has maybe 20 ears. And we can use this beamforming technique to help suppress the other voices and zero in on the voice of interest. So while the computer doesn't have the same ability that we do to pull in a lot of other information to follow a conversation in this cocktail party noise, we can somehow get around that by giving the computer more and more sensory powers with many microphones.
But in order to test our algorithms, we wanted to have something that's flexible enough so that we can turn it into whatever we wanted. So we came up with this aluminum frame cage that we can mount microphones and speakers on.
Here we are in what we call the audio cage, where we have several speakers and microphones that we're able to put up in various configurations. If you can look at the ceiling here, we have an example of one of our microphones that we use in many of our experiments. We can take these down, move them at different points. We have little laser meters that we use so we can get their positions. When we do our cocktail party recordings, we basically allow people in the room to make noise, and we have our mics in various configurations. So here's where we can do a lot of research with changing the configuration of the microphone, seeing how well we can beamform and detect sound sources, all with the goal of ultimately giving the computer this ability to perceive what's going on. With all these microphones, it has super sensing power, but ultimately we want to be able to process all that data and give it an ability to perceive and understand what's going on, so the computer can start to mimic this cognitive ability we have to interact and help other humans. One of the aspects of this project is the ability to understand what's happening in a space. In some areas of research, we call this smart spaces or smart rooms, where right now, if we want to communicate with a computer, we go up to a keyboard, we move a mouse, maybe there's a few other devices to get data into it to talk to the computer so we can get information from it. I think ultimately what we would like to do is have a room full of microphones and cameras, and when we walk into it, the computer will know who we are. And be able, instead of us logging in, it will know who we are, what we have access to. We will be able to talk to it. It could use voice recognition. If there's multiple people in the room, it'll be able to focus in on a particular person out of the room.
So Ava, the ambient virtual assistant, really is the vision of a smart room to assist people in their daily chores or to assist people who need assistance, like maybe the elderly or children. And the idea behind that is really to naturally and seamlessly integrate the computer into the environment so that you can interact with the computer in a natural way, and the computer could then understand your needs and act on them.
In our initial test bed was this idea of having an office space where the computer could understand what was going on in the room and kind of be like a virtual secretary.
So we make the connections here in the panel from the beamformer into the speech recognition system, which actually, the beamformer, of course, is our system, but the speech recognition system actually is a commercially available free software package that we use here. So when I'm outside of the beam, Ava lights on. It should not work. If I, however, move to the spot where the beam actually is being formed on, and I give the command Ava lights on, it should actually switch on the light, or I can also turn it off, of course. Ava lights off. So.
We would like to see it in homes. You know, people spend a lot of money for entertainment centers right now. We would like to see the cost down on that level, where, you know, the people would buy maybe an 8-way SMP or some computer that they can put in their house and interface that to some speakers and microphones and cameras that run throughout their house. But I think ultimately we would like to see this impact the broader range of people, similar to what cell phones have done.
We're actually envisioning something even more immersive and even less restrictive, where you don't have a monitor to look at or to gaze into a window to see that person. So we really envision a freestanding three-dimensional projection of that person.
So when you log into your computer and you want to communicate with your friend in India, with speakers, projectors, and microphones, you can maybe get a virtual presence of him. Instead of just sending an email or in a chat room, you can have a virtual space right next to you where you can see your friend, his expressions, hear the sound more clearly, or if maybe there's a whole group of people over in that room and you can hear the sound coming from the different people more distinctly because you have spatial perception or spatial distinction with your array of speakers. One of our major contributions has been a new way to render sound. For example, if I want to virtually place a sound over there in the room, how do I have to project that sound to my system of speakers so it sounds like it's actually coming from that direction?
The classical approach is actually an algorithm called wave-field synthesis, and that is actually an algorithm to recreate the sound field, the actual pressure field that has been in a room at some point, and exactly recreate it everywhere in the room. The drawback of that is that it uses a lot of speakers that have to be in a regular arrangement. That's drawback number one. Drawback number two is that it has difficulty rendering sources that are actually inside the reconstruction domain, meaning that you have sort of like a virtual curtain where the speakers that recreate the sound field separate you and the source. So we were trying to overcome these two problems, and so we came up with a completely new algorithm that is radically different from anything else that's been done in that area, and we call it multiple matched rendering, or MMR for short, where MMR really tries to solve the problem, again, physically exact, meaning we're actually going down to the equations that really govern the propagation of sound. And that lets us get away with a lot less speakers that furthermore do not have to be in a regular arrangement.
We work on recreating a 3D sound environment using just a few speakers, say 15, 14, and we target only recreating the sound correctly in one location instead of in the entire room.
So what we basically take is any sort of input stream, and we augment this information with positional information about the source, where it is located, if it is moving. So for every sample in the digital audio stream, we basically assign a position, and we feed that into the computer, and the computer then computes the activation sequence for the speakers to output to create that perception. So in this movie you can actually see a virtual sound source on the left hand side that moves around a circular array of 8 speakers with the listener indicated in red in the center. And then in the center of the movie you'll see the activation sequence that we compute with MMR to actually recreate the pressure field that is in the vicinity of the listener. You'll notice just by looking at the two movies that they don't have very much in common except for in the area where the listener is located, and that's exactly the goal we're trying to achieve. So the very right plot really shows you the difference of those two, and you'll see that there is no difference between the fields in the area where it counts, namely there where at that point where the listener is. We have filed just recently a patent on the 3D rendering system that really came out of a presentation we gave at the world's largest audio signal processing conference, and where we gained quite some attention. And after somebody from Sony talked to us very, very detailed for about half an hour, and with very probing questions, we decided it might be a good idea to get a patent on this, because we might be onto something where and that might lead to some more commercial applications than we even thought of initially.
We'll probably try to figure out different ways for spatializing sound. You know, if you take a system like this and put it in a movie theater, like for example with Jurassic Park, you had these low rumbling sounds and some like kind of things, and you felt like the Tyrannosaurus Rex was like right upon you, drooling and about to like get at you. But you got it from, like, you know, over to the left, over to the right. You were somewhere in the middle there, but there was no like Tyrannosaurus Rex really breathing down your neck, right? It was more of like hinting at that. So here you could really put the sound in the middle of the seats, in the middle of where the audience is sitting. And you would feel like there's Tyrannosaurus Rex breathing like right next to your left ear.
It really boils down to a very, very simple mathematical operation that you can do on a very low-powered computer.
We're currently targeting about a $3,000, basically a home computer. The high-end home computer will be able to process the same amount of data, but be able to do that in real time.
So this will give the computer the ability to interact virtually or create virtual worlds by able to play sounds anywhere. If we had one or two speakers, the computer would be somewhat limited in the way it could distribute sound or present sound to the people in the space. But with many speakers, we can create orchestras, let's say, where we can actually place the musicians all around you, or we can create scenarios or simulations where we have bullets flying overhead for gamers or for military training. I think the future of the laboratory is that we're going to try to play on our strength, which is the integration of these high-performance computers with these many different sensors. We want to also include in the future novel sensors. There's other investigators here that work on 3D imaging with structured light and other techniques. There's people working with stereo vision and so forth. So we want to integrate those things as well into this network, because in order to understand what's happening in a scene, just like the human does, we use multiple cues. You know, video, sound, our experience, and then we're able to understand what goes on. So clearly integrating more and more sensors, different types of sensors into the lab, and using that information in an efficient way is going to continue to be a challenge, you know, for the future.
So that's the system we ultimately envision. Completely seamless, completely natural, completely immersive.
The thing that's really the most exciting for me, honestly, about this project is that really nothing like that has been done.
One of the things, especially what we do with the rendering, is creating sound in new ways, in novel ways. We can virtually place sound anywhere, so we can do things that sound won't naturally do. One of the experiments that we've done so far is we've taken a violin part. We had a student here last summer who recorded a violin track for us, a Bach duet. So we have those two separate tracks. So we've rendered them in different spaces. So while the duet is playing, we're moving the different parts around the room. And with that spatial rendering now, it changes the way you listen to it. Ultimately, I think one of the first commercial applications for the sound rendering may be musicians and artists.
There's been quite a few artists who've worked with sort of environmental sound, but this can really push it in a completely new direction.
They can actually create spaces and then create media for this particular set of speakers or this particular environment, whereby they can create sounds that have some kind of an impact on the listener that we can call art.
Something